Welcome to this video on signal transformation, specifically focusing on time domain analysis. This process involves modifying a signal's behavior over time using mathematical operations to improve communication, processing, and system analysis. A signal is defined as a mathematical function representing a physical quantity that varies over time or space, denoted as x of t. Here, t is time, and x is the signal's value or amplitude at that moment, like your voice converted into electrical pulses. The purpose of signal transformation is threefold: signal processing, which extracts information or removes noise; communication, adapting signals for transmission; and system analysis, which observes system responses to predict future behavior. The primary time domain transformations include time shifting, which changes the signal's position; time scaling, which alters the signal's duration or speed; and time inversion, which reverses the signal's direction along the vertical axis. Time shifting involves relocating a signal to start earlier or later than its original time. The signal's shape remains identical, only the starting point changes. This operation is essentially a pure time translation, or delay. A time delay, or right shift, occurs when you subtract a positive constant t0. This shifts the waveform forward in time. Every point on the graph moves to the right, much like an echo appearing after a shout. A time advance, or left shift, occurs when you add a positive constant t0. This shifts the waveform backward in time, moving the entire waveform to the left toward negative time. This can be seen in anticipatory systems that start processing early. Key observations for time shifting: a negative sign indicates a delay or a right shift, and a positive sign indicates an advance or a left shift. Critically, shifting maintains the signal's shape, amplitude, and duration. To visualize time shifting, imagine the graph is drawn on glass. Shifting is simply sliding the glass horizontally while the amplitude axis stays fixed. You are changing the when of the signal, not the what or its value. Time shifting is used in signal matching, where receivers shift signals to find the best match with a stored template. It's also used in audio effects to create echoes and reverb by adding shifted versions of the signal back to itself. Time scaling, or stretching and squeezing, is achieved by multiplying the time variable t by a constant factor a. This changes how quickly the signal unfolds, speeding up or slowing down the sequence of events. The duration changes, but the peak amplitude remains the same. Time compression, or fast mode, occurs when the scaling factor a is greater than 1. The signal duration becomes shorter, and the waveform looks squeezed toward the y-axis. This is like listening to a podcast at 2x speed. Time expansion, or slow mode, happens when the scaling factor a is a fraction between 0 and 1. The signal duration is longer, and the waveform is stretched away from the y-axis. An example is watching a slow-motion replay. Key observations for scaling: a factor greater than 1 results in compression, making the signal finish faster. A factor less than 1 results in expansion, making the signal take longer. The signal's amplitude is unaffected by time scaling. Time scaling impacts the frequency domain. Compression increases frequency, resulting in a higher pitch, while time expansion decreases frequency, leading to a lower pitch, as shown by the examples of 5, 10, and 20 Hz signals. Time scaling has important real-world applications. In audio and video, DSP scaling controls playback speed without changing pitch. In signal analysis, stretching radio signals helps identify hidden patterns or interference signatures. Time inversion, or horizontal reversal, flips the signal across the vertical axis where time equals 0. The signal essentially plays backward, reversing the time direction so that the future becomes the past and the past becomes the future. Mathematically, time inversion is represented by substituting t with -t. This negative time index creates a horizontal reflection. For instance, a signal that originally ended at t equals 5 now ends at t equals -5. This is like rewinding an audio file. Visualizing time inversion is like seeing a mirror effect across the vertical y-axis. Every feature on the right side of the graph moves to the exact same relative position on the left side. The signal's shape remains the same, but its chronological order is flipped. Practically, inversion is a critical first step in the convolution integral, which is used to determine a system's output. It's also used in system testing to analyze signal symmetry and determine if a system is time invariant or causal. We now move to Section 5, Combined Operations. When applying multiple transformations to a single signal, the sequence of operations is vital to achieving the correct result. Order matters when combining scaling, shifting, and inversion. The golden order of operations is scale, then shift, then invert. First, compress or expand the signal relative to the origin. Next, slide the resulting signal left or right. Finally, perform any horizontal reflection last. Changing this order results in an incorrect final waveform position. Let's look at an example. Y(t) equals x2t-4. This combines both time scaling and time shifting. We must follow the correct order to accurately transform the original signal x of t into the desired final output. Step 1 is scaling. We apply the scaling factor quos a equals 2, transforming x of t to x2t. Visually, the signal is compressed, becoming 2 times narrower. The time axis effectively speeds up. Step 2 is shifting. We apply the shift to the scaled signal. We factor out the 2 in the expression x2t4 to get x2t2. The compressed signal is shifted 2 units to the right, not 4. By following the correct order, we successfully mapped the transformation. The final signal is both faster, due to the scaling, and delayed, due to the shift. The transformed state is accurate and correctly positioned. To avoid common errors, always ensure the correct order, scaling before shifting. Remember that the shift magnitude must be divided by the scaling factor when solving graphically. Finally, always apply reflection or inversion last. Time domain transformations are vital for diverse engineering systems, including medical imaging, radar and sonar systems, and vibration analysis. These applications rely on manipulating signals to gain clearer data and improve operational performance. As a key takeaway, mastering time domain transformations is the fundamental bridge between mathematical theory and real-world signal engineering. This understanding is essential for any work in signal processing. To summarize, always remember the order: scale, then shift, then invert. Shifting moves the signal, scaling speeds or slows it, and inversion reverses its direction. Thank you for watching this video on signal transformation.